Previously, we have solved systems of equations that using back substitution rather if they are in row echelon form. However, not all linear systems are actually in row echelon form. However, we are lucky that two systems of linear equations are equivalent when they have the same solution set. Therefore, we can have a system that is not in row echelon form. We can convert it to a system, an equivalent system in row echelon form by using the following operations. 1. When we write an equation, we can interchange the two equations. 2. We can multiply one equation to a non-zero constant. And 3. We can add the multiple of an equation to another equation. When we do these operations, we can still get an equivalent system from the original system. And we're going to demonstrate that later. So, this rewriting of a system of linear equations in row echelon form usually involves a chain of equivalent systems. So we can't just have a given linear system automatically to row echelon form. It might take some steps. Each of these are obtained by using one of the three basic operations mentioned a while ago. And this process is called Gaussian elimination after this German mathematician Carl Friedrich Gauss. So we're going to solve system of equations using Gaussian elimination. So first, we have this system here. We are asked to solve the system x minus 2y plus 3 equals 9, negative x plus 3y equals negative 4, 2x minus 5y plus 5z equals 17. So, how do we do Gaussian elimination to solve this system? First, it's better to write the system wherein the same variables are aligned. So I can have x minus 2y plus 3z equals 9 here. And I will have negative x plus 3y. I will leave z blank here because I don't have a z equals negative 4. And then I will have 2x minus 5y plus 5z equals 17. So at least we know that we have 3 x's here, 3 y's, and 2 z's. Now, where do we start? Now, remember that our row echelon form is in this kind of shape. So that means the first thing that we should do is eliminate those that are underneath this step. In other words, we need to remove these two terms from the two equations below. And we do that by following the three operations, which are, we either interchange the two equations, multiply an equation by a non-zero constant, or add a multiple of an equation to another equation. So, in this case, the first thing that we can do is we can easily eliminate this x. Why is that? Because this is already negative x. We can simply add the 2. Because that's one operation, adding a multiple of one equation to another equation. So, usually we would write that on the left-hand side most, although this is not really required. Now, that elimination of this x, changes in equation 2. So that means what happens in equation 2 is we add equation 1 and equation 3. So that means equation 1 does not change because it's not the one that is being changed by this symbol. And nor does equation 3. But let's write equation 3 later. So let's now do the operation indicated, that equation 2 is equation 1 plus equation 3. X plus negative x is 0. I don't need to write that. Hence, this will be blank and we achieve this, the one that we need. Negative 2y plus 3y is positive y, so I will have positive y here. And 3z plus 0 is 3z. And 9 plus negative 4 is 5. So we have a new second equation, and I'm just going to copy the third equation. 5z equals 17 because we did not touch the third equation as well. So this is already an equivalent system to the original one. However, it's not yet in row echelon form. So let's just make an arrow here. And now we'll continue. So then I will just use a different ink. So we need also to eliminate this x because the only x that we need on the top step is the one on top. So therefore, we need to eliminate this 2x. And how do we eliminate this 2x here? Remember, we can only interchange. Let's write it here on top. We can only interchange equations. We can only multiply a non-zero to one equation, or add a multiple of an equation to another equation, These are only the three things that we can do in our system. Now, if you would remember in elimination, to eliminate a 2x, we can multiply this by negative 2. So therefore, I will have negative 2x here and 2x here, and that will become 0. So what we can do is actually step or operation 3. We can multiply this entire first equation by negative 2 and then add it to equation 3. And that the result will be equation 3 already. Hence, equation 3 would be the sum of negative 2 multiplied to equation 1 plus equation 3. And that's actually operation 3. Add a multiple, the multiple is negative 2 of an equation to another equation. So this is the other equation to achieve equation 3. Thus, I just need to copy equation 1 again because I am not doing anything to it. Wait a moment. There you go. I just corrected something in the first step. So now we can now continue writing. Our equation 2 was not touched, so it will still be y plus 3z equals 5. And now our equation 3 will be the one should be touched. So we'll have negative 2 times the terms of equation 1 plus equation 3. That will be our equation 3. And again, we're doing that to eliminate this x here. So negative 2 times x is negative 2x plus positive 2x, that is 0. So we don't need to write anything. Negative 2 times negative 2y is positive 4y. And positive 4y plus negative 5y is negative y. I am not writing any more the steps because it will take up much space. And then negative 2 times 3z is negative 6z plus 5z, that is minus z, negative z, equals negative 2 times negative 9 is negative 18, negative 18 plus 17 is negative 1. At this point, you can pause the video to see if you were able to follow through the first few steps of our Gaussian elimination. Alright, so now we were able to eliminate the ones in our step here. This time, we need to eliminate this one here, which is this term. Luckily, this is positive y and negative y, so all we need to do is add the 2. And to remove this, that's affecting equation 3. Hence, equation 3 will be equal to equation 2 plus equation 3. You can write colon like what is here, or you can write equals. It doesn't actually matter. That is just actually indicating what we're doing to our system. So we'll have x minus 2y plus 3z equals 9 because we did not touch that. We're also not touching the second equation, y plus 3z equals 5. But we're touching the third equation. So now we need to add equations 2 and 3. Y plus negative y is 0. I don't need to add that, or write that rather. 3z plus negative z is 2z, so I will write 2z here, and 5 plus negative 1 is 4. So there. So now we have achieved this specific shape, and as you might have noticed, we can easily now solve alone the third equation. So solving the third equation, we will now have 2z equals 4, divide both sides by 2, therefore we will have z equals 2. And now that we have one of the equations actually solved, let's just scroll down a little bit. We can now actually see our new system, which is actually, I'm going to write it here. From here to here, I will now have x minus 2y plus 3z equals 9, y plus 3z equals 5, z equals 2, which is now in row echelon form. And now we can solve this by back substitution. So, solve the now system in row echelon form on your own, and we're going to reveal the answer in the next video.